Assalamu alaikum and welcome to a very interesting topic related to the bearing capacity of shallow foundation. In our previous lecture, we discussed about the introduction about the foundation engineering, that why foundation engineering is important in the broad field of civil engineering. We also discussed about different types of foundations which can be used in the field and different factors which can affect the footings. Now, in today's lecture, we are focusing on the shallow foundations part of the foundation engineering. It's just an introduction how we are going to find out the bearing capacities related to the shallow foundations. So in today's lecture, this is related to chapter number 2. Now we will understand what is the ultimate bearing capacity. The modes of shear failure, that how a shallow foundation will apply and exert the pressure onto the soil and how the soil will behave. Now that behavior is known as the modes of shear failure. There are 3 different modes of shear failure, like the general shear failure, local shear failure, and the punching shear failure. Then we will move towards few terms which are important to understand. For example, the gross pressure intensity, the net pressure intensity, and the safe pressure intensity. So whenever we are calling the pressure intensity or the bearing capacity, so these are used interchangeably. So don't confuse yourself about the terminologies. So those are related to the bearing capacity of the soil. Now we will briefly discuss the methods of bearing capacity determinations, then analytical methods, that how the bearing capacity was started initially with the lower bound and upper bound solutions, and then we will discuss the limit equilibrium method, and at the end of the lecture we will go in detail about the Terzaghi's bearing capacity equation, that how Terzaghi proposed a theory that how we can find out the bearing capacity of the shallow foundations. The effect of water table will also briefly discussed at the end of today's lecture. The rest of the part of this chapter will be discussed in the coming lecture. So starting with the bearing capacity of the shallow foundation, it's necessary to define what is ultimate bearing capacity. So whenever we for example, if we construct a foundation into the soil, and if P load is applied onto that foundation, so that foundation will exert some pressure which will be load per unit area. Now, the soil beneath the foundation will try to balance the load which is applied onto the soil here. Now, how much load can be taken by that soil? It is dependent upon various parameters, which is the focus of our topic for the today's lecture. So it's the least pressure which can cause kind of a shear failure in this soil is known as ultimate bearing capacity of that soil. So it's the least pressure which can be taken by this soil without reaching to the shear failure. So here is the definition if you want to note down. So it's the least pressure which would cause shear failure of the supporting soil immediately below or adjacent to the foundation. Now, what are the different modes of shear failure? That would be the next question which we'll raise in our minds. So there are three types of shear failures. For example, the general shear failure, local shear failure, and punching shear failure. Now, in order to understand different modes of shear failure, we need to look to this drawing. For example, this is the case of the general shear failure. If a load is applied here onto this foundation, and this is the ground level, it is found that there will be a portion like a wedge, which is a very rigid portion in that soil just beneath the foundation, and that is usually known as zone 1. And there is another portion or zone which is in plastic state, and this soil will have a radial or logarithmic spiral shape here. That is known as zone 2, and the zone 3 is the passive zone or the Rankine passive zone, as the soil present in the zone 2 will try to push this soil outward, and due to that push, heaving will occur from that zone 3 So if we see such type of behavior, that is termed as the general shear failure mode. And if we want to draw the pressure and settlement curve, it will look like somewhat like this. Now, when and where we will see this kind of behavior, basically there are a few characteristics. related to this kind of shear failure, this will occur in dense or stiff soils. We will see three, I would call that as so we will have a wedge here, we will have a slip surface, we will also see heaving in this type of failure. It's sudden, you can clearly see a sudden or abrupt change, a well-defined failure load, well-defined failure load can be seen in such type of modes of shear failure. Then there is another mode of shear failure which is local shear failure mode, and in local shear failure mode we might see a little bit of heaving, but we will prominently see the elastic wedge and the spiral or radial shear zone beneath the foundation. Settlement pressure versus settlement curve will fall in between the punching and the general shear failure, and we won't be able to see a defined, because it has not reached to the peak strength of the soil. So in such soils we won't be able to see the well-defined failure load. Now when it will happen, or in what type of soils it will happen, so it will happen in high compressibility soils. There is a third mode of the shear failure, and in that third mode of shear failure, that is known as punching shear failure, and this will occur in very high compressibility soils. You can clearly see the strength is very low compared to the other two modes of failures. Detailed informations are given here, so you can clearly see those informations. The dense and the stiff soils will define failure loads, and large settlements will occur in local shear failure. Tilting will also occur in the local shear failure. Failure pattern is not well defined. No bulging of the ground surface will occur in the punching shear failure. Large settlements will occur, and it occurs in very high compressibility soils. The local shear failure occurs in high compressibility, and this one occurs in very high compressibility soils. Here is also an illustration is made. For example, here this is for the dense or stiff soils. This one will occur for the high compressibility soils, and this one will occur for very high compressibility soils. If you want to draw this graph, it's already present, but if you want to draw in a different format, for example, this is the pressure and this is the settlement, and you will see initial increase in here. So this one would be the A, which is related to the general shear failure, and then You will see a kind of a strain hardening type behavior, which won't give you a specified, a well-defined failure load. Then if you want to draw the punching shear failure, so you can clearly see that's very high compressibility soil, so the strength is lowest in this type of soil and it's highest in the general shear failure types. Now we discussed a little bit about the relative density of the soils in geotech 1 and in geotech 2 as well. What is the relative density of the soils? I need a short discussion here on the relative density of the soils. We discussed here about the stiffness, high compressibility, very high compressibility, which is related to the cohesive soils. Now, we will also give you an idea that how and what type of mode of shear failure will occur in cohesionless soils. So what is the relative density? Please confirm that you can hear me and the screen is visible.
Yes, sir. Screen is visible. We hear you, sir.
Okay, thank you. Thank you for the confirmation. Now, what is relative density?
Relative, sir, relative density is the void ratio, sir.
Okay, it's good. It's related with the void ratio. That is good. Now, how we can relate that and how we can find out the void ratio? If you remember, we had an equation to find out the relative density based upon the void ratio. So we need to relate that to the void ratio of the soil, of the cohesionless soil. Okay, let me help you here. So if you remember, we were given with the Emax and the field void ratio, Emax minus the minimum void ratio. So you're right, it's related with the void ratio. This is the maximum void ratio, and here is the minimum void ratio. So this will give us the minimum density, and this will give us the maximum density. This one will give us the minimum density of the cohesionless soil, and this is the field void ratio. So that's how there are STM standards to find out the Emax and the E minimum. Anyways, now we need to discuss about the modes of the shear failure, that how we can do that. Okay, now if you see here, here is the relative density on the x-axis and depth to width ratio on the y-axis. So if we are having loose sand, so we will see the punching shear failure mode, and then if we are having medium dense sands, then we will have the local shear failure mode, and if we are having very dense sand, then we will be experiencing general shear failure mode in cohesionless soils. So that's how you can relate the mode of shear failure with the relative density of the cohesionless soils. There are a few terms which are important to understand. These are the gross pressure intensity or the Q gross. Now the Q gross is the total pressure at the base. For example, if this is the foundation here, so it's the load which is applied from the weight of the superstructure, weight of the foundation, and also the backfill soil which is placed on top of this footing. I would call that as PS. So here you can see that weight of superstructure, weight of foundation, weight of backfill soil, and if you divide that by the area, then you will get the gross pressure intensity or the gross bearing capacity for that soil. Now, as we already know that if this is the depth of the foundation, so how you can find out the Q or sigma, it would be simply unit weight multiplied by the depth of the footing. So here is the foundation. This is half of the backfill soil. Backfill. So the space is too small, so I would say backfill soil, and here Q or sigma would be gamma into D. And here that is the weight of superstructure. Now, if we remove the backfill soil or the overburden pressure from the Q gross, for example, if you want to find out the Q net, that would be Q gross minus Q, I would call that, and Q gross minus gamma into D will give me the Q net. And that's what you need to note down, because you will be using this equation in solving the examples and the problems as well. Now, for example, if the Q gross is equal to the gamma into D, then the Q net will become 0, which means that the weight of the soil excavated is equal to the weight of the structure, and settlement would be 0 theoretically. But if we further simplify this equation, that the weight is taken roughly equal to the backfill soil, then the weight of the footing and the backfill soil divided by the area will be equal to the gamma into D. And this will lead us to a simplified equation, which is the weight of the superstructure divided by the area will give us the Q net. So this is the equation which you need to remember, and we will use this equation in examples and problems as well. Now, if we apply a factor of safety to the Q ultimate, for example, if we are given with the Q ultimate, and if we divide that by, for example, 3, or I would say a factor of safety, this will give us the safe bearing capacity based upon the factor of safety we used. And we had a good discussion on why we choose a certain factor of safety, because there are uncertainty involved related to the loading, related to the soil conditions as well. Now, if you want to find out the Q safe net, then you need to subtract that gamma into D from the Q ultimate, and then you need to divide it by the factor of safety, because here this one is the Q ultimate net, and if you divide that, you can see here that we can find out the Q safe net. So if you subtract the gamma into D, then you will get the safe net bearing capacity for that soil. Now, there is another term which will be used in examples and problems, and that is the allowable bearing capacity. Now, we already know that we need to satisfy for the foundation designs the settlement criteria and the shear failure criteria. Now, in order to do that, we need to find out the Q safe, which is here, Q safe. So we will find out the Q safe first, and then we will find out the stress required to cause a specified amount of settlement, the second one here, and the maximum pressure which will satisfy these two criterias will be known as the allowable bearing capacity of the soil, because the settlement criteria has been satisfied and also the shear failure criteria has been satisfied. So the maximum pressure which may be applied to the soil such that the two fundamental requirements are satisfied. This is the minimum value. This will be the minimum value which will satisfy the shear failure criteria and also the settlement criteria, and that will be known as the allowable bearing pressure of the soil. Now, there are different methods which will be used in finding the bearing capacity. Very famous, which will be discussed at the end of this today's lecture, and which is used in solving examples and problems. This will be discussed in the next lecture, and these are known as the analytical methods, that you use certain equations where you are going to use the bearing capacity factors, where you are going to use the cohesion, friction angle, and the overburden stresses to find out the bearing capacity of the soil. There are lots of correlations. For example, with the standard penetration test, if you perform the standard penetration test in the field, so there are different correlation available with the SPT and the cone penetration test. From here will get the N value, and here we can get the sleeve fraction or the tip resistance, and even in the piezo cones we can get the pore water pressure as well. But basically this tip resistance is used to find the bearing capacity, and the N value is used in case of the standard penetration test. In Geotech 2 lab, we performed plate load test and pile load test. So we can also find out the bearing capacity from the plate load and the pile load test. There are various codes proposed by different countries or various countries there. So they can also be used to find out the bearing capacity of the soils. So we will briefly discuss the analytical methods which are giving you an idea that how we can estimate the bearing capacity of the soils. Please confirm that you can hear me and the voice is clear.
Yes, sir.
Okay, thank you. Now in analytical methods, we need to focus on the shear
Yes,
failure
sir.
criteria. Okay, thank you. So, and the settlement criteria. Okay, so there are two methods which are known as bound methods. It gives us a basis to understand how we can estimate the bearing capacity. So for example, in the lower bound method, the true load would be greater than from here what we get from the lower bound theorem. Okay, because it is giving us a estimate that this is the lower bound and the true load would be greater than the load which is corresponding to an equilibrium condition. So that's why it's the lower bound theorem or the lower bound condition. Here it is important that for the lower bound, the initial estimate was obtained for the strip footing and for phi equal to 0 condition. So it's a very simple explanation that how researchers reached to the estimation of the bearing capacity of the soil. Okay, this is the now in order to understand, let me show you this figure. In the lower bound condition, here a foundation is laid, and here, for example, this is the ground surface. So it is the load or the ultimate load which is applied onto the soil, and Q would be equal to load per unit area here. This is the overburden stress which can be found out from the unit weight and the depth of the foundation here. So in the lower bound and upper bound condition, these are based upon the theory of plasticity, and in theory of plasticity, for example, we are at the point or the soil is at the point of plastic equilibrium. And if you remember from the triaxial test, this was an equation between the major and minor principal stress. Okay, now sigma 3(1) is equal to sigma 1(2). How? For example, this is the line here. Now at this point, if you are taking two elements, element 1 and element 2, and if we make it a bit bigger here to understand the stress conditions, so this is the sigma 1, I would call that sigma 1, okay. sigma 11 and sigma 31. Now that is equal to sigma 1 2, and from there the derivation started that sigma 31 is equal to sigma 12 and sigma 11 is equal to sigma 3 plus tangent square 45 plus phi by 2 plus 2c tangent 45 plus phi by 2. If you remember, this was the figure which was taken from the Geotech 2, where we have the Mohr Coulomb failure envelope, and we draw the Mohr Coulomb failure envelope. Here is the sigma 3 and here is the sigma 1, that is C cotangent phi. This is the shear stress, and here is the sigma. Anyways, so now in this case phi is equal to 0, so tangent square 45 will be equal to 1, and we will get an equation which is sigma 11 is equal to sigma 31 plus 2c, because this one is equal to 0 and that term will be equal to 1. So we will come up with the 2c here, and that term will be equal to 1. This one is 0. Sigma 3 will come here. Now for block 2, which is here, this is the element 2, I would call that. For the soil element 2, so you can see here the sigma 32 would be equal to the gamma into d, which is this one. Okay, so this is the vertical pressure which will be exerted on top of this soil element, and therefore it has been written gamma into d. Now if you want to find out the sigma 1 2, which is the lateral earth pressure exerted onto the element or the block 2, and if we simplify that with if equal to 0, and then this term will be equal to 1, so we can come up with a simplified equation which says that sigma 1 2 is equal to sigma 32 plus 2c, or gamma into d, because sigma 32 is equal to gamma into d, and this is the equation q bar plus 2c. As we know from the equilibrium condition, the soil is in equilibrium state. Sigma 31, which is here, let me clear this thing. Sigma 31 is equal to sigma 1 2. Now if we put this equation in the equation number 2.1, so we will come up with this equation, which is giving us the q ultimate equal to q bar plus 4c. Now if we are placing the foundation at a certain depth here, then we are considering gamma into d, which is q. But if we are placing a foundation, for example here, in case of raft foundation, this q bar will be equal to 0, and we can say that the ultimate bearing capacity of that soil will be related to 4c. Now what is c? C is the cohesion of the soil. Now you can imagine that how simply we are assuming that the soil is only cohesive in nature and there is no fraction which is contributing to the ultimate bearing capacity of the soil. So it's just giving you a lower bound of, yeah, the lower estimate of the bearing capacity of the soil. Now, if we want to get the upper bound, and in case of the upper bound, the true failure load will be less than the load corresponding to a mechanism, or we can call that the upper bound condition. Okay, whatever load we are getting from the upper bound, the true failure load will be less than, because this is the upper bound and I would say this is the lower bound condition. So this is the true loading condition. Now we are just estimating the lower bound condition and we are also estimating the upper bound condition. So here is a method which is proposed, and that method is based upon a slip surface. For example, here is the foundation, and here we are given with the overburden or the surcharge pressure gamma into D. Here is the width of the foundation. This is the center point O, and this is the slip circle. And along this slip circle, cohesion is mobilized, okay, or the shear strength is mobilized. So this is the undrained shear strength of the soil. This d theta is the settlement or the movement of the soil which is occurring downwards. So if we take the work which is done internally and the work which is done externally, so the internal work is dependent upon the cohesion or the undrained shear strength of the soil, and the external work is related to the ultimate stress or the pressure which is applied, and also to the surcharge pressure. Okay, now if we equate those two, the work internal and the external, which is related to the shear strength and which is related to the loading which is applied, so you will come up with an equation which is QU equal to Q plus 2 pi Cu, and we can further simplify that as Q plus 6.28 Cu. So you can see here that in the lower bound we came with an equation which is related to Q ultimate. I would say here Q ultimate is equal to 4C. Now for Q ultimate equal to 6.28 C in case of the upper bound. So the true load here, let me explain that as well. So if for the surface loading Q is equal to 0, then it would be equal to the Q ultimate would be equal to 6.28 cu. Please confirm that the screen is visible and the voice is clear.
Yes, sir.
Okay, someone is knocking at my door,
No,
so let
sir.
me see. I don't know why. Okay, sorry for the interruption. So here we can see that the estimation, for example, this is the lower bound condition, and this is the true load condition, and this is the upper bound condition. So here we are going to get the 4C, and this will be in between the 6.28 C. Okay, it's just a rough estimate which we are going to get from the estimate of the bearing capacity. Now, limit equilibrium method is for the most commonly used method for stability of geotechnical structures, which you also saw in finding the factor of safety for the slope stability issues in Geotech 2. So we can also use the same problem, or we can solve the same upper bound solution using the limit equilibrium method by taking the summation of moments at this point. So if you take the summation of moment at this point equal to 0, so basically we are left with the ultimate pressure and the overburden pressure and the cohesion intercept, okay, the cohesion of the soil. So this is the term which is related to the cohesion, or the moments which will be created due to the surcharge, and the moments due to the ultimate pressure. So if we simplify that equation, we will reach to this equation, and if we add the shear strength of the soil term, which is equal to the undrained cohesion in this case, because phi is equal to 0, we are assuming a very simple case. We are going to discuss in Terzaghi's in detail that how we can consider both of these. So if we simplify this equation, so we will again come up with a solution which is related to the ultimate bearing capacity of Q bar 2 pi C, which is Q bar plus 6.28 of the C, and for the surface loading condition, Q bar will be equal to 0. So the Q ultimate will be equal to 6.28 C. So just to revisit, this is the upper bound solution, and here is the lower bound solution, and the true failure load will occur in between these two solutions. So it's just an estimate. Okay, now if you want to take the average of the surface loading, for example 6.28 C plus 4 C divided by 2, so you can estimate the average bearing capacity of cohesive soil when phi is equal to 0. So that was the basis that how we can get the bearing capacity of the soil. Now, Terzaghi's bearing capacity equation or the theory was used for C and phi soils, but there are assumptions which are related to the Terzaghi's theory. For example, it was originally proposed for the strip footing using the limit equilibrium method. The depth of footing should be less than or equal to B, or we can say for shallow foundations, the foundation is rigid and has a rough bottom. The soil is homogeneous. Strip foundation with the horizontal base, for example, the load so we are finding the horizontal surface, okay, and the load is acting vertically. For example, we can have certain conditions that we experience on the inclined or sloping ground, or even the load inclination with the vertical, but that will be discussed in the Meyerhof bearing capacity equation. So in Terzaghi's bearing capacity equation, he assumed that this load is vertical and the ground surface is leveled or horizontal. Okay. So these are the assumptions. General shear failure mode was assumed. We already saw that you might experience different types of shear failure modes. For example, the general shear failure mode, the local shear failure mode, or the punching shear failure mode. So Terzaghi's bearing capacity equation was only valid for this type of shallow foundation. Is the voice clear? Please
Yes, sir.
confirm. Okay. Not looking at the
Yes, sir.
messages, so we will address the questions at the end of this lecture. Okay, just to keep the flow of the lecture, and we will answer all the questions and answers which are related to this lecture or the previous lecture. So first we will have a recorded session so that it goes smoothly, that we can watch later on, and then we will go for the question and answer. So I'm not looking at those comments there, which can a little bit slow down, and you know the flow of the lecture will be disturbed. Okay, so these are the assumptions. The shear strength of the soil can be described by the Mohr-Coulomb failure criteria. Now, Terzaghi's assumed a failure surface, or the mode of shear failure or the failure mechanism. Let me see if I have drawn these here somewhere. Yes, okay. Now, let me take another color so that we can. This one, black is used, bluish. Okay, let's take the bluish one. So if here we are given with the ground surface and the foundation is placed at a depth here df. That is the load, and if you want to find out the ultimate pressure, that would be P divided by, or the load divided by area. If you want to find out the surcharge pressure, that would be gamma into df. Terzaghi said that we will see an elastic wedge here which will be rigid and which will move along with the foundation. There is another zone, so this is the zone 1, and the zone 1 can be called as elastic zone or Rankine active zone. The zone 2, which is having a logarithmic spiral, is known as the radial shear zone or the plastic zone, or we can also call that as Prandtl zone. There is a third zone, this one, and that third zone, you can clearly see that the soil is pushed towards that zone. Therefore, Terzaghi named that zone as the Rankine passive zone because the soil is pushed towards that zone. And if you recall the concept of the active and passive earth pressure, so if this retaining wall is moving this way, so this soil will be in active case, so that's why this is the active zone and this soil is pushed here, so there will be a passive resistance which will be applied onto the retaining wall, so that is giving us the passive resistance. Okay, now the friction angle which is made in here will be phi, and the load will be acting at the center of the foundation. This angle will be equal to 45 minus phi by 2. What else? Okay, this portion is a logarithmic spiral or a curved shape, and then this linear portion, the shear failure surface, is linear along this linear portion or the zone. What else we need to discuss here? If you see here, the shear strength of the soil has not been taken into consideration in Terzaghi's bearing capacity equation. However, he introduced the surcharge pressure in this derivation of the equation. Now, if we take this wedge and we bring it here to the next slide, so we can say that is A, B, or C somewhere. Okay, so if the pressure is applied from the foundation onto the soil, that can be known as the ultimate pressure, which is P A here, weight of the foundation or the soil wedge will be acting downward here. There will be a normal force which is acting onto the side wall of the failure wedge. There will be another normal force which will be acting onto the right side of the wall of the wedge. Now there will be a pressure which will be exerted vertically, and that pressure is known as PP, and this one will be acting on the left side of the wedge as well, PP, the another component, and it will be acting at phi at angle of the friction angle. This is the adhesion which is related to then the cohesion as well, so let's call that as cohesion here, C. So if you represent that as C along the left side of the wedge as well and along the right side of the wedge as well. Now PP is the passive resistance. Now if you want to find out the uh, weight of wedge, which will be the area for A, okay, which will be the area A, B, and C. So it will be half B into H and into the unit weight of the soil which is present in here. Now, how to find out the height of the wedge? So for the height of the wedge, you can say that it would be B by 2 tangent phi. So if you use B by 2 tangent phi, so here we will come up with the weight of the wedge. Okay, now if we take the summation of vertical force is equal to 0, so the vertical force which is acting downward would be Q ultimate, and also the weight, and also this is the plus sign, so it would be the weight and the forces which are acting upward would be the vertical component of the cohesion and the passive pressure which are acting here. So you can see here, so these are the vertical forces which are acting upward. So two forces, that's why in this equation 2p is used. And also the two vertical components of the cohesion, this is one vertical component, this one would be the another vertical component. Now if we take the two vertical components for the cohesion as well, so this we can call that as the equation A. Okay, this is the equation A. Now that PP which is exerted onto the this one and this one, this PP is dependent upon three things. One is the cohesion, the another one is the surcharge, and the another thing is the unit weight of the soil. So therefore this PP will be having three components, which is due to the cohesion, PP due to the cohesion, due to the surcharge, due to the weight of the soil, And now if we want to solve this equation, and if you want to find a simplified form of the Terzaghi's bearing capacity, which can be helpful to find out the bearing capacity, so what we can do, we can first assume that this PP is due to the cohesion of the soil, and then we can take the surcharge and the weight of the soil equal to 0. Then if we want to solve this equation, so we can take this PP equal to or due to the surcharge which is acting on top of the soil. Now for that we will take that soil as cohesionless and weightless. Now for the third component, we can say that this PP is equal to PP gamma, or the passive pressure which is due to the weight of the soil, and we will take the PP cohesion or the cohesion and the surcharge equal to 0. Now there is a lengthy derivation in between as well, and that has been intentionally skipped because our focus should be to understand that how we can find out the factor of safety, and which has been said here, that after evaluating these components of PP, which is not done here, and if we put all these values in the equation 1, I would say, or equation A, we will come up with a simplified equation which is derived here. So we will come up with a simplified equation which is the C and C, and that term is related to the cohesion of the soil. This Q and Q, and that term is related with the surcharge, and there is another term which is related with the weight of the soil. Now the next question will be what we mean by NC, NQ, and N gamma. Now these are the bearing capacity factors which are dependent upon the frictional angle. Okay. Now this is the equation which we got for a strip footing, where length is greater than the width of the footing. Now if we want to use this equation for different shapes of the foundation, for example, rounded, square, or the rectangular shaped foundations, then we will simply use those terms or the factors in here. Or for the square, we can use the shape factors in here, or for the rectangular we will find out this shape factor and we will use in here. Then we can go for the SC and S gamma, which is related to the third term. Okay, for the rounded here, and for the square one, and also for the rectangular one as well. So these are the shape factors which Terzaghi proposed later on to account for different shapes of the foundations. Now he made our life much easier and simple to avoid the calculations which will be involved to find out the NC, NQ, and N gamma. This is the NC, NQ, and gamma, which are the bearing capacity factors here on the y-axis and friction angle on the x-axis. For example, if you perform the direct shear test in the lab and you come up with the, for example, here C is equal to 0 and phi is equal to 30. So please kindly give me NC, NQ, and gamma values. I need 3 values for NC, NQ, and N gamma. And the reason I'm asking that it will for sure come in the exam, that the friction angle will be given and you need to find out the NC and NQ and gamma, and that can lead to the solution of your problem or even designing the foundation as well. So if you are coming up with a different value, then your answer and your foundation dimensions would be significantly different. So this is just an exercise that, for example, if we are having 30-degree friction angle, what would be the values for NC, NQ, and N gamma? Take your time.
NR will be 20, sir.
So
NQ
friction
will be
angle
25,
value.
sir.
Okay, please just wait. Okay, what is the NC value? Let me write down here. Okay, can you hear me?
Yes, sir.
Okay, so what are these values?
Sir, NC will be 29 something, sir.
Okay,
NQ
NC
will
will
be
be, I
20,
would say 29, NQ would be
will be 24 something,
24. Okay,
or
N
NR will be
gamma,
20.
it will be
20.
20. Okay, let's go for that. This is the 31, so it would be N gamma is 20. Okay, it's good. And somewhere it's 20 to 30, so I would say 24. Okay, and then we will go here. It would be somewhere here 20, and this is 30.
39, sir. 39, sir. Sorry, sir.
Okay, look, the thing is that if you miss this value, you are going to get an incorrect answer. For example, if you get a correct answer, It means that you have taken all the steps correctly. Now, if you have a different answer, I would call that, it means that you have made a mistake here. And the further we go into your solution, we will deduce the marks. So the activity is being done here just to give you an idea that from where we can make mistakes and to reduce those mistakes. Okay, now this is the figure from where we can take the bearing capacity factors. And here, if we want to find out the bearing capacity factors using the tables, which is rarely given during the exam. So if you are given with the friction angles, you can, these are the friction angles which are basically used in few examples and problems which I have highlighted. So you will solve examples in the next or in the next lecture. Okay, so effects of water table on the bearing capacity. For example, we are given with a condition and the condition says and here is the ground level. You can say that for the case 1, let me see if we can draw that somewhere here. For example, this is the case 1. So there are different cases how, and this is the equation for finding the bearing capacity Q and Q plus half gamma P into N gamma. Now we can see here that this is gamma into D and Q. So this is the second term, and this is the third term here. So the unit weight is used. For example, this is the second term. I would say that this is Q gamma into D. This is related to the second term, and here is going to be related with the third term, which is half gamma B and gamma. Okay, so this is the gamma which will be used in the third term. So if the water table is at the ground surface, so we are going to use this gamma, or the gamma here should be used as gamma saturated minus gamma of water. Okay, so this would be the effective unit weight. For the second case, because we can clearly see that this gamma has been affected and this gamma has also been affected by the water table. Now for the case 2, or I would say if the water table is somewhere here, case 2, so this second term, I would say that you can take the gamma as the gamma total or gamma bulk, and for this soil you can take as gamma saturated minus gamma of water. Now there are different cases which are involved here and different situations. For example, if the water table is below the wedge, and how we can find out the wedge here, let's go for another one here. For example, if we are having a foundation and we know that there will be an elastic wedge, and that height of the wedge can be found out using b by 2. You need to modify that equation, tangent 45 minus phi by 2. Let me confirm that as well. It's the plus, it's not the minus. So here is the plus phi by 2. Let me write that. This is b by 2 tangent 45 plus phi by 2, and this will give us the height of the wedge. And if the water table is somewhere here, then this term and this term you can only go for gamma total or gamma bulk, I would call that. And you can also use gamma is equal to gamma total or gamma bulk here as well. Now there are different conditions. For example, if the water table is present somewhere here, then how we are going to, somewhere here, I would call that as case 4. Then you can use the gamma saturated, or I would say this equation for the second term, where d1 is here. This is will be the d1, this would be the d2, and combine this would be the depth of the foundation. Okay, now in case of 5, okay, let me take a new board here. So for example, we are given with a foundation. This is the ground level somewhere here, and I would draw this as well. Let me draw that as well. So this somewhere in between, or if we don't want to draw this as well, so this would be the water, I would say case 5. Then for the first term, it will be equal to gamma total or gamma bulk, and you can use for the second term this modified lengthier equation, and this submerged can be equal to the gamma saturated minus gamma of water, and this is the depth of water table, and this h is the height, which can be find out by this equation, which is b by 2 tangent 45 plus phi by 2. Okay, this is the height of the wedge. What is gamma saturated? Is the saturated unit weight, submerged unit weight, and you can simply find out the unit weight of the saturated unit weight minus the unit weight of the water. Now these problems will be solved in coming lectures, and the Mehrhof theory will be discussed in the coming lectures as well. Thank you very much for listening very patiently. So that is the end of the lecture, which is related to the shallow foundation bearing capacity and how we can find out the bearing capacity of the shallow foundations. So these are the different zones. Today we discussed about the Terzaghi's assumptions as well. And again, let me, if you have any question, you can ask the question. So I will stop the recording.